So some people are still joining in. So beta, yesterday we discussed about the motion of the free gyro. The free gyro basically follows a star, and as the star moves in the sky in a circular fashion, moving around the pole in a circle, the same way our spin axis also follows the motion of that star. As the altitude of the star changes, the tilt of the spin axis changes, and as the azimuth of the star changes, the drift of the spin axis changes accordingly. Then we saw the formulas for tilting and drifting, the rate of change of tilt and rate of change of drift. We can obtain that from the formula. Tilting is given by 15 degrees sine of azimuth cos of latitude per hour. So we can calculate at what rate the tilt is getting changed, and drifting is given by 15 degrees sine of latitude per hour. So using these formulas, we can find out, we can get to know how fast or how slow the altitude of the star or the tilt of the spin axis is changing, the azimuth of the star and the drift of the spin axis is changing. So today we will be proceeding ahead. We will be looking at controlling this free gyro. We do not want this free gyro to move in a circular motion. So we will be controlling its motion. For controlling, we will be using some arrangements. It is known as a top heavy arrangement or a bottom heavy arrangement. So पहले इनको देखेंगे, and once we are aware of this controlling, then we will see how after controlling, how the spin axis moves. Does it motion changes or what kind of changes there? Okay, great. So ready beta, shall we start off? Okay, all right beta. In this presentation, we are going to see how do we convert a free gyro into a gyro compass. The first step of conversion is controlling the gyro, and that is done using a top heavy or a bottom heavy control. Now for controlling the free gyro, we use the force of gravity. The force of gravity is used to control the circular motion of a free gyro using two different effects. These effects are known as the top heavy effect and the bottom heavy effect. We will discuss these effects one by one. The top heavy effect is used if the rotor is spinning in anti-clockwise direction, and the bottom heavy effect is used with clockwise spin of the rotor when viewed from the south end of the spin axis. Clear बेटा, चलें आगे. Okay, great. Let's now try to understand the top heavy control in a gyro. Till now we have seen the spin axis and rotor being fitted in an arrangement of gimbals to give it 3 degrees of freedom, sets of ball bearings, gimbal rings, which give them 3 degrees of freedom. Now we introduce one more part of the gyro compass, and that part is the casing. So as you see in this diagram, you see the light blue part shown in the diagram is basically the rotor as well as the spin axis. The north and south points represent the north and south ends of the spin axis, and this light blue part in the middle represents the rotor. It is the side profile of the rotor. Now outside the rotor you see a black color casing. This is called as the rotor casing. Till now we have not seen the rotor casing in any of the gyro diagrams. But actually, when the gyro compass is made, this rotor and spin axis arrangement is fitted inside a rotor casing. Now, how is it fitted inside the rotor casing? We have to give it freedom to spin. So for that purpose, you see these dark blue parts which are shown here at the north end and at the south end, they represent ball bearings. So the spin axis is connected with the casing through these ball bearings, thus giving it freedom to spin. The casing, black color casing which you see in the diagram, is not free to spin. Only the rotor and spin axis inside the casing is free to spin. So the casing does not spin at all. However, the casing is free to tilt up and down. The casing is also free to drift east and west. Only freedom which is not available to the casing is the freedom to spin, and that freedom is provided to the rotor and spin axis through these dark blue ball bearings fitted at north and south ends of the spin axis. Now the gyroscope is made or controlled to point in one direction by attaching a weight on top of the casing. You can see this red color weight which is fitted on top of the casing. You can consider it is welded on top of the casing, and this weight is approximately close to 680 grams. The Sperry Maker Mark 20 gyro, this is one particular model of the gyro compass which is very frequently used. They use this casing for 600, they use this weight for 680 grams. This weight is fitted exactly on top of the rotor casing, and it is exactly on top of the center of gravity of the spin axis and the rotor system. So the weight is fitted on the rotor casing exactly above the center of gravity of the spin axis and rotor system. Moving ahead now. Now, since we have attached a weight on top of the rotor casing, making the top of this arrangement heavy by the 680 grams weight, that is why this arrangement is called as a top heavy arrangement or a top heavy control. When we go into the bottom heavy control, you will see that this particular weight is attached to the bottom of the casing. That is why the name as bottom heavy arrangement or bottom heavy control. Let me now show you the rotor, spin axis, casing and the top heavy weight from different angles. Till now we have seen the diagram of the rotor and the casing and the top heavy weight in this orientation looking from the side. Now in this case we are looking from the side at the rotor casing. We see the top heavy weight, red color weight on top. And this is exactly what you see on the right side of the diagram. This particular orientation, you are looking from the side of the rotor and the casing. Now if you visualize looking at this particular arrangement from the south end, you can see this eye here, and this is looking at this particular arrangement from the south end. If you look at this arrangement from the south end, the arrangement would look like this particular diagram. The point here which you see is the south end. Then you see this is the rotor, and the outer black color lining which you see represents the rotor casing, and we have the top heavy weight right on top, the red color weight. And if you look at this particular arrangement from top, you see looking from top, you have the eye placed here, and you are having a bird's eye view looking from top of the arrangement. Then this arrangement is going to look like what you see in this particular diagram, looking from top. You will be able to see the flat portion of the casing, and you will be able to see the top heavy weight exactly in the center. This is the spin axis. So this is the view, just to give you a better idea about the orientation of the rotor, the casing and the top heavy weight. So beta, I hope you have understood how this weight is fitted on top of the casing. Is it clear?
नहीं सर, ये वाला समझ नहीं है.
Okay, all right. Give me a minute. I'll show you practically with the model. Okay बेटा, ये देखो, ये हमारा मॉडल है जो कल हमने देखा था. So this is the spin axis and ये जो है ये रोटर आपको दिखाई दे रहा. And with the arrows you can see the direction. This is the south end. जो आप देख रहे हो, the direction from where you are looking, this is the south end. The north end is this one. This is the north end. North end is pointing towards me. Okay, just give me 1 minute beta. Okay, so this is the south end beta. The direction from where you are looking is the south end. You can see the rotor. It is spinning anti-clockwise, so you can see these arrows. And the casing is flat from top. It is flat from top, and then you have the casing all around this rotor. It is something like we have the grinding wheel in the workshop, or you have a portable grinder. उसके ऊपर एक safety cover लगा होता है बेटा. This casing is something like the safety cover which is fitted on top of the rotor, and on top it is flat. The weight is actually fitted here. Okay, ये देख रहे हो आप, यहाँ पे weight fitted है.
आपका कैमरा ऑन है क्या? हाँ, कैमरा ऑन है सर. Okay.
Other people,
Sir,
can
I
you see
leave
me?
the meeting, sir.
Beta, can you see me?
I'll just leave the
Yes,
meeting, sir. I cannot see you.
Okay, no problem. Just leave and join again, beta.
Okay, sir. सर, ये जो केसिंग आप कह रहे हो, केसिंग के ऊपर जो वेट रहता है, दिस इज कल हमने जो देखा था, वी हैड वन रोटर, वी हैड वन स्पिन एक्सिस, देन वी हैड वन ब्लू, रेड, ऑल दोज अरेंजमेंट. तो यू आर टॉकिंग अबाउट एवरी एकदम बाहर पे वेट अटैच रहता है या फिर ऑन एनी वन ऑफ द रिंग्स?
Okay. You are talking of that gimbal rings, beta. The horizontal ring. Okay. ये जो रिंग्स हैं बेटा, ये केसिंग के बाहर फिट होंगे. ओके, ये केसिंग के बाहर फिट होंगे एंड द केसिंग विल बी हियर. ये जो आपका रोटर है, रोटर के अराउंड ये केसिंग लगी होगी. ऐसे एक बॉक्स लगा होगा. इट इज सर्कुलर हियर एंड फ्लैट ऑन द टॉप. सो दैट इज कॉल्ड एज ए केसिंग. जो आपका हॉरिजॉन्टल रिंग है और जो वर्टिकल रिंग है वो केसिंग के बाहर फिट होगा. सो केसिंग विल बी एबल टू मूव like this, tilt up and down. Casing will be able to move like this also, but casing is not free to spin because इसकी जो spinning है that's quite fast, 6000 rpm. अभी जो थर्ड जनरेशन gyros आ रही हैं they are can be even more than 10,000 rpm. So casing जो है वो spin नहीं करता है. The rotor only spins inside the casing.
Inside the casing. Okay. So it is just like a protection cover.
Yeah, you can say that.
Okay, ठीक है.
Okay. और ये जो कवर है ये ऊपर से फ्लैट है बेटा. इट इज फ्लैट फ्रॉम टॉप एंड इसके बिल्कुल यहाँ मिडल में हमने ये टॉप हैवी वेट 680 ग्राम्स का वेल्ड किया हुआ है. सो अगर आप साउथ हैंड से देखोगे तो ये वेट यहाँ दिखाई देगा.
Alright.
अगर आप इसको साइड से देखोगे, साइड प्रोफाइल, so this is the side profile, the weight is fitted here on top.
Okay sir.
Okay, and अगर मैं ये जो केसिंग है ये आपकी तरफ कर दूं like this, so this is the flat portion of the casing and the weight is fitted here on your side.
Okay sir.
Understand now?
ठीक है सर, इजी है. बेसिकली जो अंदर का जो रिवॉल्विंग रोटर है उस पे केसिंग है, केसिंग पे एक फ्लैट देके उधर वेट फॉर प्रोवाइडिंग सम एडिशनल ग्रेविटी फोर्स समथिंग.
That's right beta, that's right.
ठीक है,
that's right.
Thank you sir, thank you sir.
Okay, let's go back to the presentation now. Okay, all right. So let's see now. We have seen how the weight is fitted on top of the casing. Let's now move ahead. Now when the spin axis is horizontal, the center of gravity of the attached weight is exactly in line with the center of gravity of the rotor, thus producing no torque at all. However, we know that our spin axis follows the gyrostar, and as time passes, the gyrostar is going to move, and as the gyrostar moves, the spin axis is going to follow it, and soon it will have some upward tilt and an easterly drift. Moving ahead now. Now please take your attention to this diagram on top. As soon as the gyro spin axis tilts upwards, you can now clearly see that the center of gravity of the weight does not act through the center of gravity of the rotor. And this weight now produces a torque in the vertical plane. And as you can see in this diagram, the torque is going to result in precession. And how is this precession going to act? Take your attention to the bottommost diagram. This is looking at the rotor and spin axis arrangement from the south end. Now you can see that the weight is now acting on the south end, pushing it downwards. This is represented by the blue color arrow in the bottom diagram. You can see the blue color arrow showing the torque which is being generated by the top heavy weight. Now when this weight acts on the spin axis, because of precession, this torque turns 90 degrees in the direction of the spin. Now we know top heavy control is used in gyro compasses which are spinning anti-clockwise as viewed from the south end. So you can see the direction of spin as anti-clockwise. So this torque which is trying to push the spin axis downwards turns by 90 degrees in the anti-clockwise direction, and now it tries to push the spin axis or precess the spin axis in the easterly direction. So the torque is resulting in a precession in the horizontal plane that tends to take the south end in the eastward direction. If the south end is pushed in the eastward direction or south end is precessed in the eastward direction, the north end is going to precess westwards. Now when the north end precesses westwards, it is going back towards the meridian. If you remember the motion of the star was drifting in the or changing its azimuth in the easterly direction, and it was tilting upwards. The star was trying to go east of the meridian. Now because of this precession, the north end of the spin axis precesses or moves towards the westerly direction, taking it back towards the meridian. So you can see we have now generated a force which opposes the eastward motion of the north end of the spin axis. Repeating once again, as soon as the gyrostar has an easterly drift and an upward tilt, this top heavy weight generates a torque which tries to push the south end downwards. Because of precession, this downward torque is rotated in the anti-clockwise direction by 90 degrees and tries to move or precess the south end eastwards, which results in the north end precessing westwards. And when the north end precesses westwards or moves towards the west, it is moving back towards the meridian. Or in other words, you can say the easterly motion of the spin axis is now checked or controlled by this top heavy arrangement. This precession is known as control precession, and in short known as PC, capital P with a small c. So समझ में आ रहा बेटा? Are you able to understand?
Yes, sir.
Okay, great, very good. Let me show you with another diagram. The same thing I'll show you with another diagram.
सर कोई वीडियो भी है क्या सर कल की तरह?
बेटा मैं ही बना दूंगा वीडियो, रुक जाओ जरा, पहले डायग्राम से एक्सप्लेन कर दूं, देन आई विल शो यू विद ए मॉडल आल्सो, डोंट वरी.
ओके सर.
Now in this diagram you can see the horizon. The horizontal black line represents the horizon and the vertical black line represents the meridian. Beta, can you mute your mics? Baiju, thank you. Initially, our spin axis was pointing towards the horizon in the meridian. That means with zero tilt and zero drift. Now we are aware that after some time the gyrostar is going to move eastwards and it is going to have a positive altitude. So our spin axis is also going to have easterly motion, easterly drifting, and it is going to have an upward tilt. So this blue color track shows the motion of the gyrostar and which is being followed by the north end of the spin axis. Now as the gyrostar has some positive true altitude or the spin axis has some upward tilt, this control precession comes into the picture, and because of this control precession, you see the weight is, as soon as the spin axis is tilted, the weight is no more directly above the COG of the rotor. It tries to push the south hand downwards. You can have a look here. The red arrow represents the torque affecting on the south end of the spin axis, and since it is moving anti-clockwise, it generates a easterly precession of the south end of the spin axis. With the south end precessing in the easterly direction, the north end has to precess in the westerly direction. The green arrow shows the direction of precession or direction of the force which is generated, and you can see that this is opposing the motion of the free gyro, the eastward motion of the free gyro, and it is taking the spin axis back towards the meridian. Now some important points to keep in mind. Number one, the control precession PC which is generated is directly proportional to tilt. When the tilt was 0, that means in this particular condition, the spin axis was perfectly horizontal. The center of gravity of the weight was directly over and above the COG of the rotor. So it was not generating any torque at all. So the control precession was also 0. Now as soon as some tilt is generated, the weight starts to act on the south end of the spin axis, generating a precession, trying to take the spin axis back towards the meridian. Now you can easily visualize that as the tilt of the spin axis increases more and more, the difference between the weight acting downwards and the center of gravity of the rotor is also going to increase more and more. So the lever is becoming more and more as the tilt increases, telling us that the control precession which is generated is directly proportional to tilt. This is a very important relationship which we will be using in our further understanding of the gyro compass. If the north end is tilted upwards, the precession caused is westerly. You can easily see from these diagrams, spin axis was horizontal here. There was no torque which was being generated because of the top heavy weight. Now in this diagram, you see a upward tilt of the north end of the spin axis, the weight acting downwards on the south end. And if you come back to this diagram now, weight acting downwards on the south end generates a easterly precession in the south end of the spin axis, and at the same time generates a westerly precession in the north end of the spin axis. Now we can easily understand that in a case if the north end is tilted downwards. The precession generated will also be exactly opposite, and in this case, the precession which is generated will be easterly. When the north end is tilted upwards, a westerly precession is generated, and when the north end is tilted downward, a easterly precession is generated. So as we can see in this diagram, the westerly precession which is generated in this particular case is going to oppose the easterly motion of the free gyro, thus trying to keep in or bring it back towards the meridian. ओके बेटा, अब मैं आपको यही चीज जो है ये मॉडल के साथ भी दिखाता हूँ। कुछ कुछ समझ में आ रहा है बेटा? आर यू एबल टू अंडरस्टैंड?
Yes, sir.
Okay, all right. Just give me a minute, I'll show you. Okay, so beta ये रहा हमारा मॉडल. This is the south end of the spin axis. This is the north end of the spin axis. This is the rotor. The direction of spin is mentioned by these arrows. So it is spinning anti-clockwise as viewed from the south end. अब हमने जो वेट लगा रखा है वो यहाँ टॉप पे लगा रखा है बेटा, ये टॉप वाला वेट है. ओके, आई एम गोइंग टू शो यू द साइड प्रोफाइल नाउ. ये मैंने आपको अब इसकी साइड प्रोफाइल दिखा दी, साइड प्रोफाइल, सो इट विल बी मोर क्लियर. जो वेट लगा हुआ है वो यहाँ पे लगा है बेटा. दिस इज द टॉप हैवी वेट. नाउ वी हैव सीन यस्टरडे कि अगर हम कोई फ्री जायरो को नॉर्थ में पॉइंट करके छोड़ते हैं, आफ्टर सम टाइम फॉलोइंग द स्टार, इट इज गोइंग टू मूव ईस्टवर्ड्स एंड अपवर्ड्स. You remember बेटा, it is going to move eastwards and upwards. तो ये जो spin axis है जो स्टार को फॉलो कर रहा है, obviously this will move eastwards and it will also move upwards. So the north end will get a up tilt. Okay up to here? Okay, all right. So अब देखो बेटा, ये जो top heavy weight था, till the time spin axis was horizontal, it was not putting any torque at all. But as soon as it gets some up tilt, north end is tilted up now, you can see this weight is now pushing the spin axis down. The weight is here, COG is here. So this much lever is generated. This much lever is generated. This weight is now trying to push the south end downwards. Okay. Now I'm going to turn it to show you how this will happen, what result it will give. See, it is pushing the south end down. Because of precession, this force will turn 90 degrees in the direction of spin and it will push the south end eastwards. This is easterly direction. So south end को जब ये east push करेगा बेटा, तो जो north end मेरी तरफ है, when the south end is pushed eastwards, the north end will be pushed westwards. So force getting applied like this pushes the south end this way. The north end comes to west. हमारा जो north end था, it was moving eastwards and upwards from the meridian. So with this force now, it is moving back towards the meridian. So are you able to understand now with this?
Yes, sir.
क्लियर हो रहा है?
Sir, but upward tilt रहेगा. Only it will move westward, but the upward tilt will be there.
Yeah, it will be there. It will be there. हमने सिर्फ अभी एक westward force generate की है, so that the spin axis does not run far away from the meridian. अगर हम इसे नहीं रोकते फिर तो ये meridian के दूर ही चला जाता काफी. अब हमने इसको रोक दिया है यहाँ पे. So this force is basically trying to bring it back towards the meridian.
It will be somewhere near the meridian, not exactly necessarily on the meridian. Means the magnitude generated will try to bring it near to the meridian, but will it be?
That's correct. हमने अभी इसका रिजल्ट नहीं देखा है. हमने सिर्फ अभी फोर्स की डायरेक्शन चेक की है कि भाई ये इसे वापस मेरिडियन की ओर लेके जा रहा है. अब इसका रिजल्ट क्या होगा वो तो अभी देखेंगे।
ओके सर।
ओके, ये तो हमें दिख रहा था कि भाई स्पिन एक्सिस मेरिडियन से दूर भाग रहा है, हमने ये मेरिडियन से दूर भाग रहा था, हमने यहाँ पे एक फोर्स लगा दी सो दैट इट गोज बैक टुवर्ड्स द मेरिडियन। इसका रिजल्ट क्या होगा वो हम अभी देखेंगे, इन विच डायरेक्शन इट विल गो नाउ, बिकॉज लॉट ऑफ फोर्सेस आर एक्टिंग हियर। एक तो टिल्टिंग और ड्रिफ्टिंग पहले ही एग्जिबिट कर रहा था बिकॉज ऑफ द मोशन ऑफ द स्टार। स्टार एल्टीट्यूड चेंज करता था, ये अपनी टिल्ट चेंज कर लेता था। स्टार अपना एजीमुथ चेंज करता था, ये अपनी ड्रिफ्ट चेंज कर लेता था। सो दो मोशंस तो पहले से ही चल रही थी। अब एक तीसरी फोर्स इन्वॉल्व हो गई है विच इज बेसिकली पुशिंग इट टूवर्ड्स द मेरिडियन। ओके, जो इसका नॉर्थ एंड है जो भाग रहा था, इट इज बीइंग पुश्ड टूवर्ड्स द मेरिडियन, बैक टूवर्ड्स द मेरिडियन। इन तीनों के कॉम्बिनेशन से अब क्या बनेगा वो हम अभी देखेंगे बेटा।
ओके सर।
ओके, वो डिटेल में देखेंगे। इंपॉर्टेंट थिंग टू नोटिस कि जब भी ये स्पिन एक्सिस का नॉर्थ हैंड अप टिल्ट लेगा तो जो प्रिसेशन जनरेट होगा वो वेस्टर्ली होगा, वेस्टर्ली। ओके, एंड अब मैं इसका आपको दूसरा भी प्रैक्टिकल करके दिखाता हूँ। व्हाट हैपन्स इफ द नॉर्थ हैंड हैज ए डाउन टिल्ट। ओके, वैसे वो डाउन टिल्ट लेता नहीं है बट वी शुड इवेल्युएट, हमें पता होना चाहिए कि अगर नॉर्थ हैंड डाउन टिल्ट लेता है व्हाट विल दिस प्रिसेशन डू। ओके, सो लेट्स सी दैट। हम पहले साइड प्रोफाइल में देखते हैं। हमने यहाँ टॉप पे एक वेट लगा रखा है, दिस इज द टॉप हैवी वेट, एंड अब हमारा जो नॉर्थ हैंड है ये डाउन टिल्ट लेता है। नाउ इफ द नॉर्थ हैंड टेक्स ए डाउन टिल्ट तो हमारा जो वेट है वो नॉर्थ हैंड को नीचे पुश करेगा। इट विल पुश द नॉर्थ हैंड डाउनवर्ड्स। नाउ द लीवर इज जनरेटेड ऑन दिस साइड, इट विल पुश द नॉर्थ हैंड डाउनवर्ड्स। इसका रिजल्ट क्या होगा, लेट मी टर्न इट एंड शो इट टू यू। ये है हमारी डायरेक्शन ऑफ स्पिन। जो हमारा वेट है वो नॉर्थ हैंड को डाउन पुश कर रहा है। इट विल मूव इन द डायरेक्शन ऑफ रोटर और इन द डायरेक्शन ऑफ स्पिन, और ये नॉर्थ हैंड को कहां पुश करेगा, इट विल पुश द नॉर्थ हैंड फर्दर ईस्टवर्ड्स। सो अगर डाउन टिल्ट होती है तो हमारा प्रिसेशन होता है ईस्टर्ली, अगर अप टिल्ट होती है तो हमारा प्रिसेशन होता है वेस्टर्ली। राइट बेटा, अप टू हियर ओके? ओके, बोलो बेटा।
When there will be down tilt west of the
Yeah.
meridian
Yes.
and we will apply top heavy weight, it will push north and downwards. No, sir. Should be upward to compensate the downward movement of north and.
ओके बेटा, हमें अप या डाउन को कैंसिल नहीं करना, हमें ईस्ट और वेस्ट को कैंसिल करना है। ये थोड़ा बहुत अप डाउन भी होगा, चल जाएगा। ओके, our aim is not to control its up and down motion, our aim is to control it east and west motion, क्योंकि अगर ये ईस्ट और वेस्ट चला तो ये मेरिडियन से दूर जाएगा और फिर ये हमारी जायरो कंपास हमें डायरेक्शन नहीं देगी नॉर्थ की। ओके, अब वो दूसरी बात है कि जब हम इसकी ईस्ट वेस्ट मोशन को कंट्रोल करेंगे तो नॉर्थ साउथ मोशन भी ऑटोमेटिकली कंट्रोल हो जाएगी, वो मैं अभी आपको दिखाऊंगा। Okay, great. So I hope you are able to understand. So let's move further. Let me go back to the presentation. Now looking at this diagram, it becomes very easy to understand that why this top heavy control is used in the gyros which are spinning anti-clockwise. The reason is that the direction of spin of the rotor must be such so as to produce a westerly precession of the north end of the spin axis when that end is tilted upwards. Because we know the motion of the gyrostar is such that it moves in the easterly direction and it has a positive altitude. That means the spin axis is moving easterly or drifting easterly and is having an upward tilt. So we want to generate a force which creates a westerly precession when tilted upwards. When the spin axis is tilted upwards, it should generate a westerly precession, bringing the spin axis back to the meridian. So this is exactly the reason. You can see in this diagram also that if the torque is pointing downwards in the southerly direction, you have a anti-clockwise spin of the rotor. This torque generates a easterly precession on the south end and a westerly precession on the north end of the spin axis. Now, if the gyro was spinning clockwise, in case of a clockwise spin, the precession generated at the south end would be westerly, and the precession generated at the north end of the spin axis would be easterly, thus taking the spin axis farther away from the meridian, defeating the whole purpose. Now, when we go to bottom heavy type gyros, we will see that in bottom heavy type gyros, the spin direction needs to be clockwise for generating the exact same effect. Now let's have a look at a bottom heavy arrangement in a gyro which is spinning clockwise. You have a similar diagram here, the only difference being that this weight is now attached at the bottom of the casing. You can see the spin axis, two ends of the spin axis represented by N and S. You can see the rotor in the middle. The black outline represents the rotor casing, and this red color weight is attached to the bottom now. Now we know after some time the gyro star is going to move eastwards and have a positive altitude, upward altitude. So the spin axis, the north end of the spin axis, is also going to have a upward tilt. Now have a look at this particular diagram, the right side diagram on top. You see as the spin axis, north end of the spin axis tilts upwards, this weight which is fitted at the bottom of the casing tries to make it vertical again. Now when it tries to make it vertical again, it is basically trying to push the south end upwards or the north end downwards. So because of gravity, this red color weight which we have fitted is trying to make the spin axis horizontal again, and due to this, it is trying to push the south end upwards and the north end downwards. Now you can have a look at the bottommost diagram. This is the south end of the spin axis where the laser pointer is right now. The weight is trying to push it upwards. The rotor has a clockwise spin. Because of the clockwise spin, the precession which is generated is in the easterly direction. The south end of the spin axis precesses in the easterly direction, and this results in the north end of the spin axis precessing in the westerly direction. So again generating a similar effect, taking the spin axis north end back towards the meridian. So if the gyro is spinning clockwise, the weight has to be fitted at the bottom to generate the similar effect. So same thing is explained here. The diagram explained the control precession generated by a bottom heavy arrangement in a clockwise spinning gyro. As the north end of the spin axis tilts upwards, the bottom weight generates a torque to bring it down. With the spin being clockwise, this torque is converted into a westerly precession of the north end, taking it back towards the meridian. So irrespective of whether we have a anti-clockwise spinning gyro with a top heavy arrangement or a clockwise spinning gyro with a bottom heavy arrangement, in both the cases, similar effect can be generated. Moving ahead now, beta. So a very important takeaway from this discussion now, the control precession which comes into the picture now because of the weight which we have fitted, top heavy or bottom heavy. This control precession, represented by PC, is directly proportional to tilt. When the tilt is 0, the control precession is 0. As the tilt starts to increase, the control precession also increases. It is directly proportional to tilt. So this tells us about the magnitude of the control precession. Now the direction of the control precession, whenever the tilt is up, the control precession which is generated is westerly. We have seen that in these two diagrams just now. The spin axis was tilted upwards and it generated a westerly precession of the north end of the spin axis. Now whenever the spin axis is tilted down, though we have not seen it till now, but in case the spin axis is tilted down, the control precession which will be generated at the north end of the spin axis will be easterly. So whenever we refer to the direction of the precession, it is always of the north end, as we are interested in the north end of the spin axis. We are not interested in the south end of the spin axis. So remember, when the tilt is up, the control precession is westerly, and when the tilt is down, the control precession is easterly. This is a very, very important relationship for understanding the gyro fundamental. So when we proceed ahead and we try to understand the motion of the gyro, we will be using these expressions. So keep it in your mind. Go ahead with your doubts, beta. Any doubts up to here?
No, sir.
Okay, great, beta, great. So go ahead, Joshua.
So by mistake, sorry.
Okay, all right. So we have seen this control precession now, beta. We have seen how this is generated and what is its direction. Now we will use this to control the gyro. So I'm taking you to the controlled gyro now. Let's go, beta. Give me a minute, I'll put up the presentation. Now we have seen the free gyro being controlled using a top heavy or a bottom heavy arrangement. Let's try to analyze what path does the controlled gyro now trace. So we are trying to understand the effect of control precession over the entire circular path which was being traced by the free gyro. We know that the free gyro, in which the spin axis was following the motion of the gyro star, the spin axis was moving in a circular fashion. You can see this blue color circle in the diagram. This represents the path traced out by the spin axis of a free gyro. The center of the circle was the pole. The gyro star was moving in circles around the pole and the spin axis was following that motion, completing one circle in one sidereal day or 24 sidereal hours. It was only under the effect of two forces. These were tilting and drifting. Tilting was caused because of the change in altitude of the gyro star. Drifting was caused because of the change in azimuth of the gyro star. Now we have introduced a third force in the picture, and that third force which is introduced is the control precession using a top heavy arrangement or a bottom heavy arrangement. Now the path of the controlled gyro converts to a elliptical elliptical path. This red color ellipse which you see at the bottom of the diagram is the path which is now traced out by the controlled gyro. Another important thing, you can see that the path has become very much smaller and shorter than before. Another important thing, this path is now traced out by a gravity controlled gyro. This is called as a gravity controlled gyro in 84 minutes. The blue circle was being traced in 24 hours, whereas the red elliptical path is being traced out in 84 minutes. So the gravity controlled gyro now traces the red elliptical path under the effect of three forces or three factors, which are tilting, caused because of change in altitude of the gyrostar, drifting, caused because of change in azimuth of the gyrostar, and control precession, which is caused because of the top heavy or bottom heavy arrangement which we have fitted. The control precession is generated by the top heavy or bottom heavy effect, and its introduction results in the spin axis tracing an elliptical path. The circular path was being completed in one sidereal day, whereas the ellipse oscillation is covered in approximately 84 minutes. The important thing to note here is that the entire ellipse is now formed below the pole, as the pole is situated at the center of the blue circle. Now, if you go back to the free gyro, you will remember that this blue color path which the free gyro was tracing was following the motion of the gyrostar, and this motion was centered at the pole. So at the center of this blue circle is the pole here, where you have the vertical and horizontal line meeting. Important thing, very important thing to note here, which we will be using later in the explanation of gyro, is that the elliptical path which is formed now by a controlled gyro, traced by a controlled gyro, the entire ellipse is below the pole. At no point on the ellipse you see the spin axis going above the pole. The spin axis always remains below the pole. So this will be used later on when we understand the elliptical motion in detail. Clear up to here, beta? Any doubts?
सर ये टाइम डिफरेंस समझ नहीं आया, वो 24 hours, ये हाउ कम दिस इज ओनली 84 minutes?
ओके, वी विल अंडरस्टैंड दैट बेटा. ये जो एलिप्टिकल पाथ है ना, इस पे अभी जूम इन करके ये पूरी मोशन को अंडरस्टैंड करेंगे. ओके. So what have we achieved by controlling the gyro? In this gravity controlled gyroscope, we have been able to restrict the circular motion of the spin axis to a much shorter ellipse. You can see now that the spin axis is much closer or remains much closer to the meridian as compared to the free gyro, which was moving large distances away to east as well as to the west of the meridian. Now after this, next we are going to discuss and analyze the elliptical motion in detail, understanding the behavior of the controlled gyro. Now, even now, when the gyro is moving on an elliptical path, which is much shorter as compared to the circular path traced out by the free gyro, the gyro has not settled yet on the meridian. Though moving very less as compared to a free gyro, it is still going eastward and westward of the meridian. So we will still need to make some further arrangement to make it point towards the meridian. For that, we will need to analyze the motion of the gyro, behavior of the gyro on the elliptical path. Questions which may be arising in our mind is that why does the controlled gyro follow a ellipse? Why doesn't it make a small circle? or why doesn't move in a, let us say, square kind of motion or a triangular motion? Why only elliptical motion? And why does the ellipse behave in this way? Why it is so small? Why does the spin axis move back from here? What is the reason? So for this, we will need to understand the balance between the three factors which are affecting our gyro now. These are tilting, drifting, and the control precession generated because of top heavy and bottom heavy arrangement. Let us now try to analyze and understand this elliptical motion of the spin axis. We have now zoomed into the ellipse, the red color ellipse which we saw in the previous slide. It is a zoomed in picture of the same ellipse. Now in this ellipse you can see three different color of arrows. You can see the red color arrow, green color arrow, and the blue color arrow. Now these three arrows represent the three forces under the effect of which the spin axis is tracing this elliptical path. What are these three forces? The first arrow, which is the red one, represents the tilting motion. Tilting motion is caused because the spin axis follows the gyro star, and as the gyro star changes its altitude, the tilt of the spin axis also changes. The blue color arrow represents the drifting motion. As the gyro star changes its azimuth, the spin axis follows the gyro star and changes its drift, which is shown by the blue color arrow. Blue color arrow is the drifting motion. And the third arrow, which is the green color arrow, represents the control precession. Control precession has been generated by applying the top heavy or bottom heavy arrangement, and it has been included or generated by us to control the free gyro. Now before we analyze and understand this ellipse in detail, it will be very helpful if we have the formula for tilting, drifting, and control precession refreshed in our mind. It will be better if you have those formulas in front of you, and you can have a look at them when you are understanding the elliptical motion. These formulas can be written down in your notebook, and it can be kept in front of you ready for reference. Okay, so beta, now when I am going to explain you about the elliptical path, have these three formulas in front of you. If you have not written them down, just take a picture and you can refer to your mobile, see these formulas. I will also show you on the slide when we go, but to have these formulas with you, so when I am explaining, you will be able to correlate it with the formula and you will be able to check whether we are doing it right or wrong. So चलें बेटा आगे, स्फीयर पे चलें, एलिप्स पे चलें. Okay, great. So let's understand the elliptical motion now. Now this can be a little tricky, so pay attention.
Picture, the elliptical one, with
You want the
tilt and force and the PC force control force.
Beta, you want the previous slide?
Yes, sir.
Okay, here it is.
Sir, drift, how the drift is outwards when above the horizon, above the pole, sorry.
Can you repeat your question once again, beta? Speak little slowly.
Sir, the drift arrow which is shown is above the pole on that picture.
Right.
It is showing outward. It should be westward. It's showing eastward, sir.
Okay, बेटा, all right. अभी देखते हैं. वैसे मैं इसको अभी एक्सप्लेन करूंगा, बट जस्ट फॉर यू, ड्रिफ्टिंग का जो एरो है बेटा, जो वेक्टर है वो ब्लू कलर का वेक्टर है, और आप देखते हो कि सारी की सारी जगह पे ये जो ब्लू कलर का वेक्टर है ये ईस्टर्ली डायरेक्शन में पॉइंट कर रहा है, राइट?
Yes, sir.
ओके, अब इसका फॉर्मूला चेक करते हैं बेटा. Formula says that drifting will be easterly if the spin axis or gyro star is below the pole. अगर spin axis और gyro star below the pole होगा तो drifting easterly होगा, right? Now I'm going back to the previous slide. Have a look at this diagram बेटा. जो red color का ellipse है, red color का ellipse, all the parts of the ellipse they are below the pole. Pole is at the center of the blue circle, so the entire ellipse is traced below the pole. If the entire ellipse is below the pole, the drifting has to be easterly. Correct?
Yes, sir.
Okay, all right. अब मैंने जैसे आपको ड्रिफ्टिंग का बताया है, मैं ये तीनों फोर्सेस आपको एक्सप्लेन करूंगा वन बाय वन. सो लेट्स गो. ओके, ये मैंने ऑलरेडी आपको एक्सप्लेन कर दिया है. द ब्लू एरो इन द डायग्राम रिप्रेजेंट्स ड्रिफ्टिंग. It is given by 15 degrees sign of latitude. The latitude for now is not changing. We are considering a stationary observer. And since the latitude is not changing, every point on the ellipse, the blue vector remains exactly same. You see the magnitude of the blue vector is the same at all the points. And also, since the entire ellipse is below the pole, the drifting is easterly. So that was the drifting part. Let's move ahead now. We now move on to the tilting vector. Let us see how the tilting vector is put in this diagram. So let's move on to the second force in action here. The second force which we are going to discuss now is the tilting motion. Now in this diagram, the red vector represents the tilting. We know that tilting is given by the formula 15 degrees sine of azimuth cos of latitude per hour. As the observer is stationary right now, there is no change in the latitude of the observer, but the azimuth of the spin axis or the drift of the spin axis is changing. At different points, you will see the azimuth is changing. Now we can see that tilting from this formula, we can see that the tilting is directly proportional to the azimuth of the gyrostar or the drift of the spin axis. So as the azimuth increases, the value of tilting will also increase. Magnitude of tilting will also increase. And at the same time, if the azimuth is 0, you see in this formula, sine of 0 will become 0, giving us a 0 tilt. That means when the azimuth is 0, the tilting will be 0. Now let's try to correlate it with the diagram. We have this vertical black line as the meridian. Now when the spin axis is pointing in the meridian, the azimuth is 0. So basically there are 2 points where the azimuth is 0. You have the point Golf and Delta. At both these points, the azimuth of the spin axis is 0, and you can see here that there is no red vector. The azimuth is 0, the tilting is also 0, so there is no red vector at both these points, Golf as well as Delta. Now, as you go away from the meridian, let's say from point Golf, we are moving further on the ellipse. Now the azimuth is increasing. The azimuth of the spin axis keeps on increasing. When the spin axis reaches at point A, it has a certain azimuth. The difference between the meridian and this point A represents the azimuth now. Now since there is a azimuth present, we will also have the tilting present. And you can see the tilting vector is present here. If you go further away from the meridian, from point A to point B, the azimuth increases still further, and with the azimuth increasing, you can see the tilting vector also increases in magnitude. At point Bravo, the magnitude or the length of the tilting vector is much more. And if you look carefully, Bravo is the point where the spin axis is achieving its maximum easterly azimuth. And you will also see that it is at this particular point that the tilting vector has got the maximum magnitude. After point B, the spin axis moves on to point C here, point Charlie. Now at point Charlie, the azimuth is reducing now because the spin axis is coming back towards the meridian. With the azimuth reducing, the spin axis, with the azimuth reducing, the tilting also reduces. Tilting is directly proportional to azimuth. So tilting also reduces, and you see the tilting vector becoming shorter than what it was at point Bravo. As you go from Charlie to Delta, at point Delta, the azimuth becomes 0. So going from point Charlie to point Delta, as the azimuth keeps coming down, the tilting vector also reduces in magnitude and eventually becomes 0 at point Delta. Now from point Delta, the spin axis moves westwards. So as it moves westward, the westerly azimuth increases now. The maximum westerly azimuth is achieved at point Echo, and you can see here that at point Echo, the magnitude of the tilting vector is also maximum. From point Echo, the spin axis tries to go back toward the meridian. The azimuth is decreasing. Remember always, we are considering the quadrantal azimuth here. We are not considering the three-figure notation azimuth. When we discuss about gyro, the azimuth is always considered or referenced in the quadrantal notation. So echo to foxtrot, the azimuth reduces, and you can see that the magnitude of the tilting vector also reduces. Foxtrot to golf, the azimuth comes down, becoming 0 eventually at golf point. So similarly, the tilting also keeps on coming down, reducing, decreasing, and eventually becomes 0 at point golf. So at every point on the ellipse, the magnitude of the tilting vector matches with the magnitude given to us by the formula. Now, another important thing with the tilting, we are aware that the tilting is upwards east of the meridian. If you refer to the tilting formula, you will see the direction. Tilting is upwards east of the meridian because east of the meridian, all celestial bodies, they rise up in altitude, and tilting is downwards west of the meridian. So if you have a look in the diagram, we have the meridian as this vertical black line. At all the points which are east of the meridian, you see point A, then point B, Bravo, then point C, Charlie. All these 3 points, the tilting vector is upwards. And if you go west of the meridian, you have 2 points in the diagram, point Echo and point Foxtrot. At both these points, the direction of the tilting vector is downwards. So telling us that the magnitude as well as the direction of the tilting vector is correctly shown, displayed in the diagram. Okay, now moving on to the third vector in the diagram, that is the control precession vector, the green color vector in the diagram. Now we know that this green vector, which is the control precession, is proportional to tilt. One is that it is proportional to tilt. Second is when the tilt is upwards, the control precession acts westwards. And when the tilt is down, the control precession acts eastwards. Now in this diagram, you see we have the horizon at this particular location. You can follow the laser pointer. This is the horizon. Whenever the spin axis is on the horizon, the tilt is 0. Whenever the spin axis is above the horizon, we have a upward tilt, and whenever the spin axis is below the horizon, we have a downward tilt. So let's try to check this control precession vector starting from point A in the diagram. Now point A in the diagram is exactly on the horizon. That means the tilt is 0. If the tilt is 0, control precession will also be 0. That's why you don't see any green vector at point A. After point A, the spin axis moves along the ellipse and reaches up to point B. Now at point Bravo, we have some upward tilt. Now because of this upward tilt, you see the control precession is now generated. The green arrow is present here, and this control precession is acting in the westerly direction. We know when the tilt is up, the control precession acts westwards. From point B, we move up to point C. Now at point C, the tilt has increased further. As the tilt has increased, you can see the magnitude of the control precession has also increased. The green vector has become bigger. Direction is still westwards because at any point above the horizon with a upward tilt or a positive tilt, the direction of control precession will always be westerly. We move further along the ellipse and we reach to point delta. If you observe carefully, point delta is the highest tilt point in the elliptical path. So maximum tilt is present here at point delta, and you can see that the control precession is also the strongest, having the maximum magnitude. Anywhere in the ellipse, the maximum magnitude of control precession is also at this point due to the fact that control precession is directly proportional to tilt. Direction is westerly as we are having a upward tilt. Now from point delta, as you move along the ellipse to point echo, at point echo the tilt has reduced now. Now with the tilt reduced, the magnitude of the control precession also reduces. From point echo, we reach up to point foxtrot. Now this point foxtrot is on the horizon. When the spin axis is pointing on the horizon or in the horizon, the tilt is 0. If the tilt is 0, the control precession will always be 0. It will also be 0. So you don't see any green vector here. The control precession is not present at this particular point. Moving further, when you go from foxtrot to golf. Now golf point is having a downward tilt. Means it is below the horizon. Spin axis is pointing below the horizon. The tilt is down. Now with the tilt down, the control precession is generated now, but it acts in the easterly direction. Because we know from the control precession formula or expression that the control precession acts easterly whenever the tilt is down. You can see the green color vector acting here in the eastward direction. Golf is the only point which is below the horizon in this entire ellipse, and it is the only point where the control precession is acting in the easterly direction. So now we have checked the application of all the three forces: the tilting, that is the red vector, drifting, the blue vector, control precession, the green vector. We have checked these vectors at all the points: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf. And we have seen that as per their respective formula, the vectors are applied correctly. Now we will try to combine all this information and we will try to understand why does the spin axis move on an elliptical path. Till now we have seen all the forces individually. Tilting, drifting and control precession all have been seen individually, and we have checked the accuracy of these vectors. Now we will try to understand their combined effect and how that effect results in the elliptical motion which we are seeing on the screen right now. So let's start off. When the spin axis is placed horizontal, pointing towards true north, It is at this particular location where the laser pointer is right now. The spin axis is horizontal, so it is pointing in the horizon. The spin axis is pointing northwards, so it is pointing in the meridian. And the point where the laser pointer is right now, this is the point where the spin axis is. So when the spin axis is placed horizontal pointing true north, its position in the ellipse is at this particular point represented by N. Now let us try to analyze the forces acting on the spin axis right now at point N. At point N, tilting will be 0 because tilting is proportional to azimuth. The azimuth right now is 0, spin axis is pointing in the meridian. So azimuth 0, tilting will be 0, there is no red vector. At point N, the control precession will also be 0 because control precession is proportional to tilt. And right now the spin axis at point N is pointing in the horizon. We don't have any tilt, 0 tilt. No upward tilt, no downward tilt. The tilt is 0. If the tilt is 0, the control precession will always be 0. So we don't have any tilting, we don't have any control precession. What about the third force, drifting? Drifting is given by 15 degrees sign of latitude and it is constant all over the ellipse. So at point N also, we will have the same drifting vector. So drifting will be present and it will be present in the same direction and magnitude as it is present on all other points. So we will have a easterly drifting. Because of this easterly drifting, the spin axis is immediately pushed to east of the meridian. So easterly drifting pushes it eastwards. Now be careful and pay your attention. As the spin axis moves eastwards, it has come east of the meridian now. That means a easterly azimuth is generated. If a easterly azimuth is generated, the tilting vector is now going to come in the picture. Tilting is proportional to azimuth. So as easterly azimuth is generated, we will have upward tilting. This upward tilting is going to push the spin axis upwards. So it will start to move above the horizon. You can follow the laser pointer. It is moving upwards now because tilting has come into play. Now as it moves upwards, it is generating some tilt also. As the tilt is generated, control precession will also get generated. And since we have a upward tilt, the control precession will be westerly. So this westerly control precession is becoming stronger and stronger as the spin axis tilt is increasing. The westerly control precession is becoming stronger and stronger as the tilt is increasing. And as the spin axis reaches point B, the control precession has become so strong that it has become equal and opposite to the drifting vector. You see right now at point Bravo where the laser pointer is, drifting is acting easterly. The blue vector represents drifting. Control precession now has become equal and opposite to drifting. Now since control precession and drifting are equal and opposite, the spin axis will not have any easterly or westerly motion. They will both cancel out each other. At point Bravo, the tilting is maximum. It is the strongest and it is upward tilting. So from point B now, the spin axis moves upwards. It neither goes to east nor goes to west. It moves upwards. Now as soon as it moves upwards, what is going to happen? As it moves upwards, the tilt is going to increase further. If the tilt increases, control precession is going to become more powerful and it is going to overpower the drifting vector. When the control precession becomes more powerful, it tries to bring back the spin axis towards the meridian. We have a westerly control precession, so it takes the spin axis in the westerly direction towards the meridian. So you see after crossing point B, the spin axis starts to move westwards. Now when it moves westwards, the change what is happening right now is Moving westward, the azimuth of the spin axis is reducing. With the azimuth reducing, the tilting is also becoming weaker and weaker. So you see at point Charlie, the azimuth has reduced as compared to point Bravo, and because of this reduced azimuth, the tilting vector has also become much smaller as compared to what it was at point Bravo. So under the effect of these three forces at point Charlie, it moves further westwards. The tilt keeps on increasing, making the control precession more and more stronger. And as it keeps on closing into the meridian, azimuth reducing, the tilting is also reducing. So eventually it reaches at point delta. Now what happens at point delta is, at point delta, the azimuth is 0 again. With the azimuth 0, the tilting also becomes 0. That's why the red vector, the tilting vector, disappears. There is no tilting here because the azimuth is 0. Drifting vector is the same as it was at any point on the ellipse, easterly with a certain magnitude. But the control precession vector is the most powerful, is the strongest at this point. Why it is the strongest? Because the tilt is maximum at this particular point and control precession is proportional to tilt. Now with the control precession acting in the westerly direction much more stronger than easterly drifting, the spin axis now crosses over to the western side. As it crosses over to the western side, we have the westerly azimuth increasing now. The azimuth is increasing. So with the azimuth increasing, the tilting again comes into the picture. But since we are west of the meridian now, the tilting is downwards. West of the meridian, the tilting is downwards. So when you go west of the meridian, tilting acts downwards. That's why you see the spin axis starts to go down. As you go down, the tilt reduces, and as the tilt reduces, the control precession also becomes weaker and weaker. And at point eco, the control precession has become so weak that it is now barely equal and opposite to the easterly drifting. So again at point eco, the easterly drifting and the westerly control precession cancel out each other. The tilting is the strongest here because the azimuth is the maximum. So this westerly maximum azimuth generates maximum downward tilting, and from point eco, the spin axis goes vertically down. As it goes vertically down, the tilt reduces further. With the tilt reducing, control precession also becomes weaker and weaker. Control precession becoming weaker, the easterly drifting takes over and it starts to push the spin axis towards east. And going like this, the spin axis reaches at point Foxtrot. At point Foxtrot, the tilt is 0. With the tilt 0, control precession is 0, so you don't see any green vector at this point. The only two forces acting now is easterly drifting and the downward tilting. Under the effect of these two, the spin axis goes below the horizon now. You see, drifting is easterly, but the tilting is downwards, so it goes below the horizon. As it goes below the horizon, we have a negative tilt now, a downward tilt, and a downward tilt results in easterly control precession. So as we go below the horizon with a downward tilt, we have easterly precession, we have easterly drifting, and at point Golf, where the laser pointer is right now, you see both these forces, that is drifting as well as control precession, acting in the westerly direction. They quickly pull the spin axis to east of the meridian. So both of these forces, the drifting as well as the control precession acting in the easterly direction, pull the spin axis to east of the meridian. As you go east of the meridian, upward tilting comes into the picture, pushing it upward. So the spin axis reaches back at point A. At point A, there is no control precession, easterly drifting and upward tilting takes it above the horizon and further eastwards. As it goes above the horizon further eastward, westerly precession is generated, and at point B, the westerly precession becomes equal and opposite to the easterly drifting. So you can see now, under the balance of these three forces, the spin axis starts to trace this elliptical path. Go ahead with your doubts, beta.
Why this control precision is not there at the point F, G and A?
Okay, beta. Control precession is there at G. G पे बेटा आप देखो ब्लू वेक्टर के साथ ना एक छोटा सा ग्रीन वेक्टर भी आगे दिख रहा है. सो कंट्रोल प्रिसेशन इज प्रेजेंट एट G. गोल्फ पे प्रेजेंट है. फॉक्सट्रॉट एंड अल्फा, यहाँ पे कंट्रोल प्रिसेशन प्रेजेंट नहीं है बिकॉज कंट्रोल प्रिसेशन इज प्रोपोर्शनल टू टिल्ट, एंड अल्फा एंड फॉक्सट्रॉट बोथ आर ऑन द होराइजन एंड द टिल्ट इज 0.
But the tilt arrow, why the tilt arrow is there, sir? F and A.
ओके बेटा, जो एरो देख रहे हो आप ना, वो टिल्टिंग का एरो है. You note the difference between tilt and tilting. Tilt basically means how much above or below the horizon you are. Tilting means what is the direction in which you are going. So alpha पे tilting तो है, the tilting is upwards, but the tilt is 0 बेटा. Getting clear बेटा? Okay, all right. और जो हमारा कंट्रोल प्रिसेशन है, इट इज नॉट कनेक्टेड टू टिल्टिंग, इट इज कनेक्टेड टू टिल्ट. जितनी टिल्ट होगी उतना ही कंट्रोल प्रिसेशन होगा. और कोई डाउट्स आ रहे हैं बेटा? और बताओ.
सर ये जो नॉर्थ सीकिंग का जो कर्व है, ये स्टार्ट्स फ्रॉम N at horizon and goes to B. So when it comes back, it will follow a same curve directly from E to N, right?
No. It will not go from E to N beta. It will go in this A, B, C, D up to golf, and it will keep on following this elliptical path only. It will never go back to N now. It will keep on following the elliptical path. हमने शुरू N से इसलिए किया था because we kept our spin axis on the horizon and in the meridian. So that is where we want it. But after you leave it, it now follows the elliptical path. It is not going to come back to November now.
Okay.
Okay.
Sir, if this spin axis pointing below the horizon will be there also, no? Drift will be there also.
Drifting will be there beta. Drifting will be there at all the points.
Oh, but the drift will not be there at the horizon.
Drift is also there, पर हमने यहाँ पे drift को कहीं भी consider नहीं किया है because हमें drift is basically the azimuth beta. Okay, how much far away from the meridian you are. So delta और golf point जो है वहाँ पे आपकी जो azimuth है या drift है वो 0 है. Other than delta and golf, बाकी सारे points पे azimuth is present. Okay, all right. Great beta. Very good. So let's wrap it up.
Sir, drifting तो हमारा natural movement of the free gyroscope है ना, and
Yes,
we are
tilting.
controlling the drifting using PC.
That's correct beta. That is right. Tilting और drifting दोनों natural causes थे, natural phenomena थे. सिर्फ control precession जो है is a man-made force जो हमने यहाँ पे involve की है to reduce the motion of the spin axis. हम अभी भी इसे पूरा कंट्रोल नहीं कर पाए हैं. एक और स्टेप में अभी हम इसे पूरा कंट्रोल करेंगे, but we have reduced the motion quite a bit.
And over here, even the tilting has been reduced because of the PC. It is not letting it go further away from the
Yes.
meridian. So
Exactly.
basically,
That's right.
हाँ sir.
That's
So
right.
basically, the drifting is independent in this. Drifting is independent. It will keep acting all through. And what forces will keep changing is azimuth, tilting, and PC.
Yes, that's right, beta. That's right.
ठीक है sir.
Okay, great. As it goes below the horizon here, below point F, it goes below the horizon. We see that easterly drifting and easterly control precession, they are both pulling it in the eastward direction. So the motion from Foxtrot to Golf to Alpha is quite fast, as the easterly drifting and the easterly control precession both are pushing it in the easterly direction. So this explains the easterly motion below the horizon, and we have now seen why does the spin axis move in this elliptical path. Now, once it reaches back at A, it keeps on oscillating under the effect of these three forces in this elliptical motion, completing one oscillation in about 84 minutes.
Sir,
Go ahead, beta.
excuse me. Sir, from G to A, is there tilt? Tilt will be there, no, sir?
Yes, beta. At point Golf, you have a down tilt, and this down tilt is reducing slowly. At point A, the tilt is 0.
That it will be horizontal, spin axis will be horizontal.
Yes, at point A, it is pointing in the horizon and it's perfectly horizontal.
Okay, sir. And G to B, the tilting will be in a maximum pace.
At Golf, tilting is 0. As you start to move eastwards, tilting will increase.
Okay, sir. Thank you, sir.
Okay. We have understood the elliptical motion now. Now the beauty of this elliptical motion is that when the spin axis is moving on this elliptical path, oscillating on this elliptical path, at any particular point, let us say the spin axis was at point Charlie, you try to disturb the spin axis. You apply a force, let us say a upward force you apply, and you take the spin axis to this particular point where the laser pointer is right now, and you leave it here. The beauty of this motion is that as the spin axis moves now under the effect of these three forces, you will see after about 3 oscillations, it is going to come back to the same elliptical path. So wherever you take it, you disturb it and you take it someplace else, it is going to oscillate and come back to the same elliptical path. The same is true if you try to push it inside of the ellipse. Let us say at point C, you apply a downward force, you put the spin axis here. If you put the spin axis here, again you will observe that it will move under the effect of these three forces, and slowly it will go and match with the ellipse, and then it will keep on oscillating where the elliptical path is. So this is basically a stable equilibrium. The spin axis has attained this stability because of the combination of these three forces. The tilting, drifting, and control precession are balanced in such a way that if you try to disturb the spin axis at any point on this ellipse, sooner or later it is going to come back. As soon as you leave it, it is going to come back to this elliptical motion. So this is now called a gravity controlled gyroscope. In short, it is also called a controlled gyro. So in this gravity controlled gyroscope, now we have been able to restrict the circular motion of the spin axis to a much shorter ellipse. However, this gravity controlled gyroscope is still cannot be used as a compass because the axis still does not point along the meridian. but keeps on oscillating along the elliptical path repeatedly. It is not settled in the meridian. It is going eastward of the meridian, even though it is coming back, then going westward of the meridian, again coming back, but still not steady and pointing towards the meridian. So it is still not suitable for our purpose, our use as a direction finding instrument or a gyro compass. Now what we need after this is some form of damping. You see, this is oscillatory motion now. We have a oscillatory motion. Now one good thing which we have achieved is, irrespective of wherever our gyro star is, the spin axis is not going to follow the gyro star. It is going to follow this elliptical motion. The gyro star has gone out of the picture now. The spin axis is going to follow the elliptical motion, this particular oscillation. And now we need some form of damping so that we can dampen these oscillations and make the axis, the spin axis, settle in equilibrium along the meridian or in the meridian. So some form of damping is required which can dampen these oscillations and make our gyro steady in the meridian. It should settle in equilibrium in the meridian. Okay, beta. Great. So we have done the controlled gyro. So now I will show you how this is dampened. So that's the final procedure in the gyro compass. So before that, let's take a short break, beta. Okay, beta. Let's move back. So आगे वापस. Great. So let's see the damping of the gyro, beta. Damping is the last tricky part in the gyro. So let's go. Let's open our presentation. In this presentation, we are going to see how the elliptical motion of a gravity-controlled gyroscope is dampened and how it is converted into a north-seeking gyro compass. We have seen earlier that a gravity-controlled gyroscope cannot be used as a compass because its axis does not point along the meridian. The axis keeps on oscillating along the ellipse repeatedly. Thus, some form of damping is needed to dampen the oscillations and make the axis settle in equilibrium along the meridian so that we can use it as a direction finding instrument. Now in damping, the controlled ellipse becomes a spiral inwards towards the equilibrium position where the axis is going to settle down, and also what is important to note is that if the axis is disturbed from this settling position, the axis has the capability to return back to the equilibrium position. Now this is achieved by damping the ellipse. This damping is possible in two different ways. The ellipse can be dampened in azimuth or it can be dampened in tilt. Now the damping in azimuth method is used or employed in bottom heavy gyros. Bottom heavy gyros are the ones which are rotating in a clockwise direction. In azimuth damping, the damping precession, this is the fourth force which will get involved into a damped gyro, north-seeking gyro. It is known as a damping precession, in short known as PD. In a gravity controlled gyro, we had introduced the control precession, which was known as PC. Now for damping the ellipse, we will include or introduce a damping precession, which is known as PD. When you use damping in azimuth method in bottom heavy gyros, which are rotating clockwise when viewed from the south end, the damping precession always acts towards the meridian, which basically means that whenever the spin axis goes east or west of the meridian, this damping precession tries to bring the spin axis back into the meridian. So in this case, the damping precession will be either in the easterly direction or the westerly direction. Now the damping in tilt, which is the method used in top-heavy gyros. Top-heavy gyros are the one which are rotating in the anti-clockwise direction when viewed from the south end. Now in this damping, the damping precession, this is the additional force which we have introduced when we dampen the ellipse. PD acts towards the horizon. It basically means that whenever the spin axis goes above the horizon, the damping precession tries to push it downwards back to the horizon. And whenever the spin axis goes below the horizon, it tries to push the spin axis upwards towards the horizon. So basically, damping in tilt method uses a damping precession which opposes the tilt in all the cases. If you have an upward tilt, it acts downwards, opposite to the tilt. And if you have a downward tilt, it acts upward, opposite to the tilt. Now, most of the gyro compass made by the makers are anti-clockwise gyros. Viewed from the south end, they are anti-clockwise gyros. So the damping method which is used in those gyros is damping in tilt. So we are going to understand this damping of the gravity controlled gyroscope by using the damping in tilt method. So let's go into the damping of the ellipse by using the damping in tilt method, which is used in top heavy gyros. These are the ones which spin anti-clockwise looking from the south end. So you can see a diagram of the rotor, spin axis and the casing. Now in this diagram, the dotted lines which you are seeing, these dotted lines basically represent the rotor. You are looking at the rotor and spin axis arrangement from the south end. This circle in the center of the diagram which you see, it represents the spin axis. The spin axis is going into the screen and it is coming out of the screen towards you. You are looking at the spin axis from the south hand side. So the end of the spin axis which is going into the screen is the north end of the spin axis, and the end of the spin axis which is coming out of the screen towards you is the south end of the spin axis. So we have the spin axis going into the screen and coming out towards you, with the north end into the screen and the south end towards you. So obviously, if the spin axis and the rotor is oriented in this particular way, you will be able to appreciate that in this case, the right side of the diagram will show the easterly direction. It is represented by the alphabet E. So the right side of the direction of the diagram shows the easterly direction, and the left side of the diagram will show the westerly direction. When you are looking at the rotor and the spin axis from the south end, you will be able to see the entire rotor. So the dotted line represents the rotor, and the solid line which you see outside, the solid line represents the rotor casing. Now, as I told you before also, that this rotor casing is connected to the rotor via ball bearings. So the freedom to spin is provided to the rotor and the spin axis by these ball bearings. The casing is not free to spin. The casing, however, is free to tilt up and down, and the casing is free to drift also in the easterly or westerly direction. But the casing is not free to spin. Another important thing, you see the top part of the casing is kept flat. The top part of the casing is flat. So as we have seen that the casing will not be spinning, it is not free to spin. The flat portion on top is going to stay here only. It is not going to spin clockwise or anti-clockwise in any which direction. It is going to stay horizontal and at the top only. Now, when we generated the control precession, we placed a weight exactly on top of the center of the rotor. So we placed a weight where right now the laser pointer is. So the weight was placed here to make it a top heavy gyro. The weight was exactly on top of the center of gravity or the center of the rotor. Now to generate damping precession, we again place a weight on the casing of the gyro compass, but this weight which we are placing now, it is much smaller as compared to the weight which was placed to make it top heavy. In fact, that weight, to be specific, is about 680 grams, and this weight which we are placing now, the weight which is highlighted in yellow color, this is the weight which we are placing now, is much smaller, and it weighs only 17 grams. So the rotor casing carries this small weight, 17 grams on top. It is exactly in the same plane as the rotor. It is in the plane of the rotor, but you can see it is offset slightly to the west of the spin axis. You can see this is the westerly direction, the left side, and the small weight which we are placing is not on top of the rotor, but it is slightly offset to the westerly direction. So this yellow weight which you see on top of the casing, slightly offset to the west, weighing 17 grams, is the weight which we use for generating the damping precession, for damping this in tilt. You see the same diagram which we saw in the earlier slide. It shows the rotor, the spin axis pointing towards you. You are looking at it from the south end, the north end of the spin axis going into the screen. We have the casing represented by the solid black lines, and we have a flat portion on top of the casing. We have a small weight, 17 grams to be precise, fitted on top of the casing in the plane of the rotor, but slightly offset to the westerly direction. Now, this is where the critical part of damping begins. So please pay your attention to understand this particular part. If you understand this one slide, the damping fundamental or the damping principle will be very much clear in your mind. Now let's assume that this particular gyroscope having the spin axis pointing in the north-south direction, the spin axis, because of any reason, let's assume the spin axis starts to tilt. How does it tilt? The north end of the spin axis has started tilting upwards. Now if the north end goes upwards, obviously the south end of the spin axis will go downwards. Now let's say it keeps on tilting like this. The north end is tilting upwards and the south end is tilting downwards. Now if it tilts by 90 degrees and you are looking at it from the same direction, if it tilts by 90 degrees, this is how it is going to appear. You see, this is the spin axis tilted by 90 degrees. The north end of the spin axis, which was initially pointing into the screen, has gone upwards and it will be now pointing vertically upwards. You see, this is pointing vertically upwards now. This is the north end of the spin axis, and the south end, which was initially pointing towards you, it has tilted downwards, and you can see in this diagram the south end is tilted downwards. This is the south end now tilted downwards, and in this condition you will be able to see the top part of the casing. So you are actually looking at the flat portion, the top part of the casing, and this yellow weight which is fitted on top of the casing in the plane of the rotor, this dashed line which you see, the dashed line which you see in the diagram, which I am showing by my laser pointer, basically represents the plane of the rotor. And our weight, the yellow color weight, is fitted in the plane of the rotor and it is slightly offset to west. Okay, you see the spin axis is now vertically up and down, and you can see the weight has been offset to the westerly direction. So this is how the weight is. Now with the spin axis horizontal, that means the first diagram, the damping weight has no effect at all. It does not generate any effect at all because the damping weight is in the same plane as the rotor. It is offset to the west, so it will try to move the western part of the casing downwards, but the western part of the casing it will try to push downwards, but that's not possible because the casing is fixed and not free to spin. The casing is not free to spin, so it is not able to push the westerly side of the casing down. So with the spin axis horizontal, that means the first diagram on the left hand side, the damping weight has no effect at all. But let's assume now that the spin axis has tilted by 90 degrees. That means the second diagram which you see on the right hand side. When the spin axis tilts, the damping weight starts exerting a torque. So if you concentrate on the right hand side diagram, the north end is now pointing upwards and the south end is pointing downwards. The damping weight is offset to the west. So now this damping weight tries to push this part of the casing down. It is basically as if it is trying to push the south end of the spin axis as shown by this arrow. So our damping weight, the yellow color weight, being offset to the west, now tries to push the south end downwards. You see, in this particular case, the center of the rotor is here. The left part of the casing becomes heavier because of this weight fitted, the right part of the casing is lighter. So this weight tries to pull down the westerly part of the casing. And if you see its effect on the spin axis, it is trying to push the spin axis in this particular direction. Let me show it with the arrow. So you can see this arrow appearing on the screen now. This is how the damping weight is trying to push the south end of the spin axis. Now, to understand the effect of this particular force, let me take you to diagram number 1. So we will see how does this force acts on the south end of the spin axis and what does it result into. The spin axis is tilted up and down only, but just to understand the effect of the force, we will now generate or draw this force in the left hand side diagram, diagram number 1, and we will be very easily able to find out there how does this force affect our spin axis. Right now in the right hand side diagram, you see the north end is tilted upwards by 90 degrees and the south end is tilted downwards. And this damping weight is trying to apply a torque or a force on the south end of the spin axis as represented by this arrow. So let's show this in diagram number 1. You can see the arrow in the left hand side diagram. This is how the arrow is trying to push the south end of the spin axis when the north end is tilted upwards. So with the north end tilted upwards, this is how the offset weight or the damping weight is trying to push the south end of our spin axis. Now we know our rotor is spinning in the anti-clockwise direction. Looking from the south end, it is spinning anti-clockwise. So let me show you the direction of the spin and we will be able to then see how does this force actually move the spin axis basis the gyroscopic precession. So this is the direction represented by the maroon color arrow in which our rotor is spinning. It is anti-clockwise direction when viewed from the south end. So now the gyroscopic precession says that this force which is being applied to the south end of the spin axis is turned by 90 degrees in the direction of the spin and will be applied like this. So the force is applied in this particular way now. You see the upward arrow highlighted by the laser pointer. This is how the force gets applied to the south end of the spin axis. So this force tries to push the south end of the spin axis upwards. Now obviously if it is trying to push the south end upwards, the south end goes up and the north end will have to come down. So you can now see that we have generated a force which is trying to bring the north end downwards. Okay, so beta, before you ask your doubts, let me show this thing all to you using that demo. So I'm just going to close down the presentation and going to show you the demo with the model. Just a minute. Okay, all right. Now pay attention here, beta. यही चीज जो हमने अभी presentation में देखी. You see, this is the rotor, this is the spin axis, casing is flat on top. You are looking at the south end. We have a weight which is fitted offset to the west. So this is the westerly direction. Okay, this is the westerly direction. This side is east. So the weight is fitted somewhere here. Okay. Now let us assume that the spin axis has got a up tilt. सो अब टिल्ट हो गई बेटा, ये नॉर्थ हैंड जो है ये पूरा 90 डिग्री ऊपर टिल्ट ले गया है. Weight is fitted on this side, offset to the west, this side. So this part of the casing becomes heavy. Because this is becoming heavy, because of gravity, the weight pushes this part down. If it is pushing this part down, it is basically applying a force on the south hand in this way. How does this force act? For that, I will pick it up a little bit to show you the direction. This force is going to move 90 degrees in the direction of spin, and it is going to push the south hand up. If the south hand goes up, the north hand comes down. So you see, जैसे ही north hand up जाता है, जो ये offset वाला weight है, ये north hand को नीचे ले आता है. So अब समझ में आया बेटा?
Sir, ये for this direction of the added weight pushing the south end in eastward direction.
Right.
The tilt has to be 90 degrees.
No. 90 डिग्री तो सिंप्लीफाई करने के लिए मैंने आपको बता दिया. अगर थोड़ी टिल्ट होगी तो भी ये पुश करना शुरू कर देगा, बिकॉज दिस पार्ट इज हैवियर ना, सो इट विल स्टार्ट पुशिंग इट डाउन इवन इफ द टिल्ट इज लेसर. However, जितनी ज्यादा टिल्ट इंक्रीज होती रहेगी उतना ही ज्यादा डैम्पिंग प्रिसेशन बढ़ता जाएगा, and it will be maximum at 90 degrees.
Okay, sir. Because the small added weight, the direction of force by gravity is downward, but because it is attached to the assembly, so that is why resultant direction is eastwards.
Yeah, that's right, beta. See, it is offset to the west. You have a up tilt. The western part becomes heavy. It pushes the south hand this way, turns 90 degrees in the direction of spin, and pushes the south hand up, bringing north back.
Okay, sir. Thank you, sir.
Okay. अब मैं इसका ऑपोजिट भी आपको करके दिखाता हूं कि अगर नॉर्थ हैंड डाउन टिल्ट लेता है तो फिर ये क्या करेगा. सो लेट अस सी दैट द नॉर्थ हैंड हैज टेकन ए डाउन टिल्ट. सो वेट इज ऑफसेट टू द वेस्ट, इस साइड में लगा हुआ वेट. नॉर्थ ने अब डाउन टिल्ट ले लिया, सो वेट इज ऑन दिस साइड नाउ. इट मेक्स दिस पार्ट ऑफ द केसिंग हैवियर. नाउ इफ दिस पार्ट इज हैवियर, it'll try to bring this part of the casing down, or in other words you can say it is pushing the north hand in this way. अब ये behave कैसे करेगा? So let me show you. You can see these arrows. If it is pushing the north hand this way, it will turn 90 degrees in the direction of spin and it will push it up. So you see, if the north hand goes up, this damping weight pushes it down. If the north hand goes down, the damping weight pushes it up. We have generated a force which opposes the tilt at all times. Up tilt है तो ये इसे नीचे लेके आता है, down tilt है तो ये इसे ऊपर लेकर आता है. So are you able to understand this, beta? Okay, great. Because this is a very tricky part and very difficult to understand from the book. So अगर ये समझ गए हो तो बढ़िया बेटा. So now you just have to remember that we have generated a force which opposes the tilt at all times. So अब इस force को हम अपने ellipse में apply करेंगे and we will see the ellipse getting dampened by making a spiral. So shall we do that? Go back to the presentation.
Okay, sir.
Okay, all right, beta. Let's see that. Okay, so this damping precession which we have generated is proportional to tilt. It is acting downwards when the tilt is up and it is acting upwards when the tilt is down. This is what we have seen. Now let's fit it in the ellipse. So let's now understand under the effect of these four forces, how does the spin axis or the gyroscope behave? Now this damping precession converts the ellipse into an inward moving spiral. As you can see in the diagram now, you can see the diagram. there is a spiral motion which is moving inwards. So this inward moving spiral goes in this particular way and eventually settles down at this particular point, S. So this is the settling point where the spin axis finally settles down. Now in this diagram, you see 4 total forces are there, which we just now discussed. That is tilting, drifting, control precession, and damping precession. So we have added up only one new force here, which is the damping precession. And we know that the damping precession is proportional to tilt, and it is always opposite to the direction in which it is tilted. If the spin axis is tilted upwards, the damping precession is down, and if the spin axis is tilted downwards, the damping precession is up. Let us now try to understand how the introduction of this new force, that is the yellow color force damping precession, converts the elliptical motion into an inward spiral. The first 3 forces which you see, the red color force tilting, the blue color force drifting, and the green color force control precession, are exactly behaving in the same way as they were behaving in the elliptical motion. The only new addition is the yellow color force, which is the damping precession. Now we start from point A. This point A is exactly the same point A which was there in the ellipse. And at this point, the spin axis is pointing on the horizon. There is no tilt. If there is no tilt, there is no control precession and there is no damping precession. The only 2 forces acting here are upward tilting and eastward drifting. Under the effect of these 2 forces, the spin axis moves eastwards and increases its tilt. As the tilt increases, going from point A to point B, both control precession and damping precession are generated. At point Bravo, the control precession cancels out the easterly drifting and the damping precession opposes the upward motion of the spin axis. As the spin axis goes from Bravo to Charlie, you see the tilt increases all the more. With the tilt increasing, the new force which is added up, that is the damping precession, keeps on becoming stronger and stronger, and it opposes the upward motion of the spin axis. Now this results into point C being lower than what it was in the elliptical motion. In the ellipse, there was no downward force, no yellow force. So the spin axis was moving upward without any restrictions, and it was reaching up to a much higher tilt at point Charlie here. But in the spiral motion now, because of this yellow color vector pulling it downwards, this point C is at a much lower tilt as compared to the ellipse. So you see, the spiral motion has started to go inwards in the ellipse. Moving from Charlie to Delta, this downward acting damping precession brings the spin axis quickly to Delta position. In the elliptical motion, the spin axis would have gone farther away from the meridian with a greater azimuth to the westerly direction. But since this yellow color force is pulling it downwards, it goes from Charlie to Delta very, very quickly. So this Delta point is also much inwards as compared to the ellipse. This Delta point is much closer to the meridian as compared to the Delta point of the ellipse. Now, as it moves from Delta to Echo and from Echo to Foxtrot, at point Foxtrot, we see the new force, that is the damping precession, acting upwards. So this has pushed the point Foxtrot upwards as compared to the ellipse. In the ellipse, this point Foxtrot would have greater down tilt, but because of this upward push from the damping precession, it has come much closer to the horizon. So you can see now with every subsequent oscillation, the spin axis is coming closer to the meridian and ultimately coming at point S, which is its settling position. This point S is the equilibrium position of our spin axis. At this point X, all the four forces are perfectly balanced out. The easterly drifting is perfectly cancelled or countered with the westerly control precession, and the upward tilting is perfectly countered or balanced by the downward damping precession. Is that clear up to here, beta? Any doubts coming in?
Sir, yeah, at F, can you explain this drifting and PC direction?
Okay, at F beta, Foxtrot?
हाँ sir.
Okay. देखो बेटा, drifting at every location will remain easterly, 15 degrees sign of latitude. So it will remain easterly because the entire ellipse is below the pole. So it is exactly same as it is on any other point. And control precession, we know control precession is proportional to tilt, and control precession acts easterly when the tilt is down. Control precession acts westerly when the tilt is up. Yes. So since F point is the only one which is below the horizon, this is the only point where control precession is easterly.
Okay, sir. Thank you.
Okay. Great, beta. Very good. This leads the spin axis on an inward spiral, finally making it settle at this point S, where all the four forces, that is tilting, drifting, PC and PD, balance out each other. Now the point where it settles has to be the point where all these four forces cancel out each other. Because if any of the force is not cancelling or not balanced, then there will be some resultant force acting on the spin axis and it will not settle there, it will move to a new location. So it has to settle at a point where all these four forces balance out or cancel each other. This is a stable equilibrium because if you try to move the spin axis out of this position, the forces will get misbalanced, it will get disbalanced and will guide the spin axis back to the settling position. Let's say, for example, the spin axis has settled here and you apply a additional force in this particular direction and take it somewhere here and leave it. Now once you leave it here, the balance of all the four forces will get mismatched, it will get disbalanced again, it will start moving on a spiral path like this and eventually come back and settle at this particular location only. So wherever you take and leave the spin axis, it is going to move on a spiral path and then eventually come and settle down at this particular location only. So this basically converts the gravity controlled gyro into a north-seeking damped gyro compass, which we can now use on ships as a direction finding instrument. Now one question which is sometimes asked in the examinations also, written as well as orals. Why is gyro less effective at higher latitudes? Go ahead, beta.
So, sir, for making gyroscope not seeking, we have to extend both damping and that weight against the tilt.
राइट बेटा, राइट. मैं बताता हूँ आपको. लेट मी फर्स्ट एक्सप्लेन दिस, फिर मैं आपको बताता हूँ कि क्या क्वेश्चन आता है और कैसे आंसर करना है. Now with our understanding of these four forces, we can very easily appreciate why the gyro becomes less effective and almost loses its directive force when we go close to the poles in higher latitudes. You can easily understand it. We have seen in our explanation that the free gyro is controlled by PC, control precession, and is made north-seeking by introducing PD, that is the damping precession. Now both of them, PC as well as PD, are proportional to tilt. That means if there is no tilt, there will be no PC and there will be no PD. Now the tilt is generated by tilting, or you can say the rate at which the tilt is generated is known as tilting, and tilting reduces as we proceed to higher latitudes. Why does it reduce? Let's look into the formula. The tilting formula is 15 degrees sine of azimuth cos of latitude per hour. Now you see, as the latitude increases, cos latitude value becomes lesser and lesser. And at the pole, if you put the latitude as 90, the tilting value becomes 0 because cos 90 is 0. So tilting is maximum at the equator, reduces as we go to higher latitude and becomes 0 at the pole. Now when tilting is 0, that means tilt will not be generated. The rate of change of tilt is 0. That means tilt will not be generated. If tilt is not generated, PC and PD will not be generated. And if PC and PD does not exist or they are not there, the gyro cannot become a north-seeking damped gyro compass. So with increasing latitude, cosine value decreases, reaching to 0 at poles, resulting in lesser and lesser tilting and hence lesser tilt. In the absence of tilt, as well as absence of PC and PD, the sensitivity and accuracy of the gyro compass is greatly reduced in latitude 70 degrees and above. Now there is one more point to consider here, that is, there are a few errors in the gyro compass which we will see in the coming presentations. The errors like CLSE. CLSE is course latitude speed error, also known as steaming error, and the second one is latitude error. They become excessively high, leading to an unreliable and lesser effective gyro. So these are the two reasons why the gyro becomes very less effective in higher latitude and loses its directive force. Clear, beta? This is clear? Okay, all right, beta. Great. So now, beta, in this topic, आपको जो question मिलेंगे, written exams you can get a question. Explain how a free gyroscope is converted into a north-seeking damped gyro compass. Okay, so this can be a full 25 marks theory question. अब इस question को आपने 3 parts में divide करना है, all leading to about 8 marks. The first part is you are going to explain a free gyro. So if you can make that gimbal ring diagram and explain it in a paragraph, that is 1/3 of the answer. Then you explain a controlled gyro. So if you can make the ellipse and write a few lines, 3-4 lines explaining that ellipse, that takes the second part. And third is the spiral. So third part is you can make the spiral and write a few words. So these 3 diagrams and a little bit of explanation will take care of the full gyro theory. Okay, how do we make a north-seeking damped gyro compass? Free gyro, controlled gyro, and the damped gyro. 3 diagrams. First the gimbal diagram, second the elliptical ellipse diagram, and third the spiral diagram. So इन तीनों को आप एक बार प्रैक्टिस कर लें, and if you answer that, that would be excellent. Okay. Actually रिटर्न्स के लिए तो अगर मैं आपको यही 3 चीजें भी बता देता तो that would have been enough. बट जायरो कंपास में बेटा ओरल्स में भी बहुत सारे क्वेश्चन पूछे जाते हैं. सो दैट्स व्हाई आई वांटेड टू एक्सप्लेन टू यू कि इनका बेसिस क्या है. अब एलिप्स बना के उसको याद करके बनाना इज वन थिंग, बट टू अंडरस्टैंड हाउ द स्पिन एक्सिस इज मूविंग ऑन दैट एलिप्स इज व्हाट इज क्रिटिकल. एंड इफ यू गेट स्टक विद समबडी हु इज टीचिंग जायरो कंपास इन ओरल, तो वो तो सर्टेनली बेटा आपको इसमें लेके जाएगा. And once you understand this, then you will be able to answer him well. So, did you find it effective, beta? समझ में आया कि कैसे ये काम करता है actually? Okay, all right. Okay, great, beta. So that's all for today, and we stop it here. अब बेटा मैं आपको ना एक वीडियो लिंक आज भेजने वाला हूँ. कल का जो हमारा टॉपिक है, टुमारोज टॉपिक आर गोइंग टू बी जायरो एरर्स. सो देयर आर 2 एरर्स, डैम्पिंग एरर एंड द स्टीमिंग एरर. तो मैं आपको एक स्टीमिंग एरर का वीडियो भेजने वाला हूँ. सो जस्ट वॉच दैट वीडियो ओवर द डे. व्हेन यू आर कंफर्टेबल, जस्ट वॉच दैट वीडियो. दैट विल टेक केयर ऑफ द स्टीमिंग एरर. मैं आपको डैम्पिंग एरर कराऊंगा और उसके बाद हम इन एरर्स पे बेस्ड न्यूमेरिकल क्वेश्चन जो है वो कल शुरू कर देंगे. सो होपफुली वी शुड बी एबल टू कंप्लीट द न्यूमेरिकल क्वेश्चंस टुमारो. राइट बेटा? Okay, all right. So that's all for today from my side, beta. Anything you want to ask or share? Great. So we call it off and I'll see you tomorrow. Bye-bye.
Thank you, sir.